Hi, thank you very much, everybody, for being here. It is our pleasure to welcome Professor Thomas Hales from the University of Pittsburgh, who's been doing some remarkable work, not only in traditional mathematics research, but also pushing the boundaries of formalized mathematics and formal verification, which we view as an integral part of computer science and informatics. And anybody who's done any formal proof, any significant formal proof, knows that most of the time this brings its fair share of tribulations before it brings any joy, right? So when we hear that Tom is nearing the completion of the formalization of the proof of the Kepler conjecture, something that initially was estimated as taking 20 years, I think we should take notice, right? Because I think this could have ramifications not only for mathematics, but also for computer science. So I'm really pleased that he's here. I only hope that this lecture, which is only 1 hour, will do justice to the effort and all the good work that's been going into this. And without any further delay, I just let Tom tell us about the lessons learned from the formal proof of the Kepler conjecture. Thanks, Tom.
Thank you very much. It's an honor to be able to speak to you today. The problem that I want to talk about is a formal proof of a result in mathematics. There's a result called the Kepler conjecture. Last year it had its 400-year anniversary. So this is a very easy mathematical question to ask. You have congruent balls in ordinary three-dimensional Euclidean space, and you want to pack them together as densely as possible, so you fill the largest possible fraction of space. And there's a very obvious candidate, and that is the cannonball arrangement. So this is the pyramid that you see of cannonballs at war memorials. It's the arrangement of oranges that you see at the fruit stand. And the conjecture is that this fills the largest possible fraction of space. So this is about 74% of space. This problem goes back to Kepler. The history seems to be that he was walking home one night and it started to snow. He started to examine the six-sided structure of the snowflake. And he wasn't a real believer in the atomic theory, but he had some sort of notion of atoms, and he tried to explain the structure of the snowflake by how to pack congruent balls together, and arrived at this conjecture as the best possible packing. So his line of reasoning started with snowflakes, but then he turned to, it seems that it was pomegranates that inspired the idea of close packing, that he looked at how pomegranates were packed together and looked at their structure. So the first proof of this theorem was obtained in 1998 by me and a graduate student, Sam Ferguson, working with me. It went a long time before publication. This was not what I had hoped, but a team of referees was assigned to check the proof. The proof was about 300 pages. The proof involved some long computer calculations. And in the end, the report that I got back from the editor and referees was that they were fairly certain that the proof was correct, but they were exhausted, and they were going to publish it anyway without complete certification. At one point during this process, I received a rather strange letter from an editor saying, "We will go ahead and publish this as soon as you convince us that it is correct." And I thought the purpose of the paper that I had submitted was to convince them that the paper was correct. And I started to think about if somebody isn't convinced by a mathematical paper, what extra evidence could you present that would lead them to believe more strongly in the correctness of a mathematical proof. And it was this line of thought that led me in the direction of formal proofs in computer science, where you put the axioms of mathematics into a computer, and then you don't allow anything out until you've checked every single logical inference. So with that, I started a project that I called the FlySpec project. The name comes from taking the formal proof of Kepler and just looking for a word that starts with F and ending in K with a P someplace in between, and taking the meaning of FlySpec to be to scrutinize in great detail. That's what we intend to do. This is a big project to do a formalization of this size. My estimate at this point is that we're about 80% through, and I'd like to report on that project today. So just to give you a little bit of an outline of the structure of the proof before I talk about formalization. There's a text part of the proof. As I said, that's about 300 pages long. That's been rewritten into a book called Dense Sphere Packings that sort of gives the blueprint of how the formal proof should be written. And then there are 3 separate computer programs that contain, these are custom written computer programs for the proof. The first is a graph generator. You take different clusters of spheres, and you take the vertices. These are finite clusters of spheres, and the vertices of the graph are the centers of these spheres, and then you give a rule for when you connect the different edges together. And this replaces a continuous problem of sphere packing by a discrete problem, and you want to classify the possible graphs that can come up. And one part of that is to then use a computer program to generate all the possible graphs, and there are about 100,000 graphs that come up as part of the proof. And then you want to rule out all of the other cases other than the ones that you want to show to be optimal. So you have a nonlinear optimization problem associated with each graph. Nonlinear optimization can be NP hard, but I took a linear relaxation of these nonlinear problems and used linear programming methods. So sorry, there are about 25,000 graphs, and then there are about 100,000 linear programs that come up as part of the solution. And then the third computer program does nonlinear inequality proving. I'll be spending quite a bit of time in this lecture talking about how that piece of code works and the work that's been done towards the formalization of that piece of code. And then finally, in the end, you have to put these pieces all together. So I use a proof assistant, which is a piece of software that contains the axioms of mathematics and the rules of inference. And this software is called HOLLIGHT. HOL is an acronym for higher order logic. This is was developed by John Harrison. I'll say a word about the history in the next slide. One of the nice things about this particular theorem prover that I like as a mathematician is that the trusted kernel of the system is extremely small. There are only about 400 lines of computer code that you really need to trust, and after that it's becoming self-checking, that it's proving theorems about just using this trusted core. Of course, if you put an axiom or a rule of inference, if you code that up incorrectly, then you're going to get garbage out. But that's all expressed. There's about 100 lines giving the type system, about 100 lines of code saying what the terms are in the system, about 100 lines saying what the theorems are in the system, and then a little bit more saying what the axioms are. And that's the whole system. And then the rest is all just built on top of that. It has a simple type system. I won't say much more about that. This is a system, so some systems are designed in a way to try to look as much as possible like a mathematician would write mathematics. This looks a lot more like just programming in the objective camel programming language. There's one feature that will be important for us as I talk about the verification of the computer code. Some systems are designed in a way that if you verify an algorithm, you can then run the algorithms, and the results of running the algorithms, these verified algorithms, then become theorems in the system. But this system is designed in a way that calculation is second class, if you want. Everything has to always go back through the logical kernel, so that you're always, when you're verifying an algorithm, you're actually restructuring the algorithm so that the output of the algorithm is a theorem, and that you're producing the proofs as you go. So every separate execution of the algorithm produces a new proof of the results that you need along the way to do the verification. One of the reasons I picked this particular system is it has a large library of results already in real analysis, which was useful in this project. Anybody from here, of course, knows the significance of higher order logic. It goes back to a logical system designed by Dana Scott for constructing, one of the things is the logic for constructing recursive functions through fixed points. In 1972 at Stanford, Milner gave the first computer implementation, a system also called LCF, that's a proof checking program. Then he moved here the next year and built a new system. And this became the center of development for the software. Mike Gordon was a postdoc here. Later he moved down to Cambridge. He was interested in hardware verification, and he changed this LCF system to what is now known as the HOL system at Cambridge. Development continued there. John Harrison in 1990 joined that lab, and he then became the person who implemented this particular version of HOL that I use in my proof verifications. So the first lesson, international collaboration works. So this was good news for me. I come from a background of pure mathematics, working mostly individually on papers, perhaps occasionally working with a graduate student. This was a much bigger project for me, and it wasn't clear at all whether I would be able to work with a large group of collaborators, but that's turned out to work remarkably well. So I was pleased to find out that some of these people have migrated here. Stephen Obua is here. Mark Adams is not here today, but he has been the manager of the project and is now here. So in 2009, I organized a workshop in Hanoi. I had been there on sabbatical and talked a little bit to people then about it, and a few people had really caught on to using Holide, and I realized it might be able to do it on a much larger scale. So we organized a workshop. Here's me and John Harrison, the designer, implementer of the system in Hanoi. This is the next year, the people that were left in the workshop. But this has really been crucial for the success of the program. It's someday we hope to be able to just scan a paper on the way to the referee and have it go through a formal proof system. That's technology under development. We had a brainstorm before my lecture about our dreams of what the next features will be in these systems. But the technology is under constant improvement, but it's still a lot of work. Of course, I come at this from a mathematical point of view, a mathematical background, but good software development practices help, and having a good manager, Mark Adams, has really helped our project along. It's been very important to structure this program around a clean mathematical proof. The original proof is quite difficult to read. I've been quite surprised by the amount of time, the fraction of my time that I've had to spend at the purely mathematical end that had nothing to do with the formal proof part, just getting a text script that is capable in theory of being formalizable. And I think you would have a similar experience if you just pick any random published paper in a mathematical journal. It really makes a big difference to spend a lot of time before you do the formalization to present this in the best possible way. There are other things that we learn just day to day doing this, that there are now over 15,000 theorems in this system. To use a theorem, you refer to it by name. And of course, there are famous theorems that you can guess the name of, like the fundamental theorem of calculus or the prime number theorem. Well, this doesn't get used in the proof, but you know, the mean value theorem. These you can guess the name, but to use the others and to know their names is a major challenge, and search is becoming a bigger and bigger factor as the complexity of these systems increases. So as part of doing this formal proof, I've had to rework every aspect of the original proof. Just to give a few examples, there's a section that's based on, as I said, you need to classify planar graphs with certain properties. Georges Gontier, I understand he spoke here last year, and he'll be coming again for a visit next month. When he did the formalization of the four-color theorem, he used a data structure called hypermaps that turned out to be extremely convenient for representing planar graphs when you do formal proofs. And when I heard of how he did that, I immediately switched everything over in my own proof so that it relies on hypermaps. I think I've got a slide here. So a hypermap is just it's an abstraction of a planar graph, but you just start with a planar graph. You add what are called darts at each angle of the graph. This is a finite set of points if you start out with a finite graph. And then there are three different permutations on this set of darts that you can define. The first permutation comes from the faces. You just trace each face around, and that gives a permutation of the darts. The second permutation is the node permutation, where you just follow each node of the graph around the darts at that node. And the third is an edge permutation, where you sort of go to the opposite end of the edge and cross over to the other side. And it turns out that if you compose these three maps, you always get the identity. And so then you can define a hypermap to be a finite set together with three permutations that compose to the identity. And then you can express everything that you need to know about the graph theory in terms of these sets and permutations. So that's how the current proof is done. Another thing is that I changed the partition of space that gets used in the proof. My original decomposition of space was quite complicated. Marshall has published a paper where he proposes a new approach to proving the Kepler conjecture. In fact, I've received an email from him where he tells me he's now completed a second proof of the Kepler conjecture. So We don't have a paper yet, but it's possible that we'll soon have a second proof. But if you look at, so on the top, I've just shown what's called the Voronoi decomposition of space. The points represent the centers of the spheres, and then you draw a polyhedral region around each, where you take around each point the points that are closer to that center than to any other sphere center. And adapt, so that, if you use that decomposition of space, you get a rather bad bound on the density of sphere packings. So you need to find different decompositions. The one on the left here is a decomposition that I use in the original proof. And on the right, you see the decomposition that's used by Marshall. Visually, they look quite similar. They're sort of disk things and triangle things. But in terms of even though the decomposition that you get in the end looks quite similar, the rules that I give describing this decomposition are much more complicated than the rules that he gives describing this decomposition. So it turns out to be much easier in practice, especially when you want to do this all formally. So just other things that have been added, much more automation's been added. When I did the original proof, when I talked to mathematicians, I would ask them, you know, I think maybe I can prove the Kepler conjecture, but I'm going to need to use a computer. Would you accept a computer proof? And the answer that I got most frequently was something along the lines, if you can prove it using a computer, do it, but only if you have to use a computer. And I sort of got the feeling that I should be using a computer as little as possible. Of course, when you go to a formal proof, it's the opposite extreme, that you're now putting everything into a computer. And so rather than trying to do things minimally, I'm now trying to use as much automation, as much, use the computer as effectively as possible. Here's just an example of how proofs change. One result that you need, a fairly obvious lemma in geometry, is that if you have a convex spherical polygon on a unit sphere, that the perimeter is maximized when it's just the equator. You just want to make it as big as possible. So something like that in the original proof would have been just stated without any proof at all as an obvious fact. Then when I went to write it down, I first wrote it down by a deformation argument where you take each point and then you move it towards the equator and you see that the perimeter is monotonic and the equator is getting bigger. But then I finally settled on a very short, slick proof that there's this duality of spherical triangles where you can, for each point, you can take the polar great circle, and theorems in spherical trigonometry come in dual pairs in this way. And if you just write down the dual to this perimeter estimate, it's saying that areas are non-negative. So this then becomes very elementary. So you do have to formalize a little bit about duality, but it becomes very elementary. The formal proof, I said, is about 80% complete. The text part is now within, it's a 300-page book. It's now within 300 lines of being completely formalized. So it's starting to, even though it's not quite there, it's starting to feel like we're getting very close. Some people have the attitude that you should develop tools that allow things to just be, they view it almost as cheating if you change the mathematical proof and translating it from the mathematical text into the formal proof. And I sort of have the other extreme of an attitude that you should really, as you do the formal proof, you should really be transforming it and improving it and adapting it for the new medium. And as part of this, just this focus on exactly how this proof goes and working out tools to make this as simple as possible, I've seen that other related conjectures in mathematics can be solved by some of these same tools. So this has been one very pleasant byproduct of this work. One of them is what's called Weierstrass full contact conjecture. Here's a picture in the plane of what happens. If you take the tightest possible packing in 2 dimensions, it's just this hexagonal honeycomb arrangement. And in this arrangement, each disk touches exactly 6 others. And if you have any arrangement in which each touches 6 others, it just has to be this arrangement. Now in 3 dimensions, you can get 12 as the maximum number of congruent balls that you can touch, a 13th in the center. This wasn't proved until the 1950s. It goes all the way back to a famous discussion that Newton had. But there's a lot of free play. There are many, many different arrangements that have exactly 12 touching. And only 2 of those arrangements correspond to close packings. But the conjecture was that if you require every sphere to touch exactly 12 others, then that completely rigidifies things so that you get one of the close packings. That was the conjecture. And using some of these same decompositions of space and methods, I was able to give a proof of this last year. And another result that follows along similar lines is a conjecture of Karol Bezdek called the strong dodecahedral conjecture. I said in an earlier slide what the Voronoi decomposition of space is. You can do this in any number of dimensions. There was a conjecture about the smallest possible surface area of a cell. And the conjecture was that it's just a regular dodecahedron. And that, again, I was able to prove last year using some of these methods. A nice lesson about code verification is that there's one sure way to ensure that you won't execute a bug with a piece of code, and that is to delete the code. Tobias Nipkow, Gertrude Bauer did the formal verification of the graph generator. That was one of the first big successes of this project. And in doing so, he came to visit me in Pittsburgh. Nipkow visited me in Pittsburgh while he was finishing this project. And he would come into my office every day and tell me what new pieces of code he had deleted from the original project. And by and by, the proof was complete. There was a lot of code optimization that really wasn't needed, and it just was complicating the project. So I've been rather aggressive about this. Nobody knows exactly how much code was in the original proof. One estimate is 187,000 lines of code. That includes a lot of code duplication. It's now well under 10,000 lines of code, and I don't need to explain how that simplifies a formal verification project. And at the same time, the execution is sped up quite a bit. We can now run all of the code for the verification in less than a day. One final lesson is, so this project, well, yeah, I originally estimated it would be a 20-year project. We're 80% through. We've probably put in at least that many work years. But we see that it still is not nearly ambitious enough in the sense that someday we really want these systems to work for mathematics. And we want these systems to provide useful tools that mathematicians use on a regular basis. And as we approach the completion of this project, I just see how much we still need to do before that's a reality. So Yeah, so the example I give at the bottom is, you teach an analogy that you teach a graduate course with 10 students and you think you have a big course, and then you look at the calculus courses with 1,000 students and you think they have a big course, and then you look at what they're doing at Stanford with 160,000 students, and then you realize how small your course was after all. So I want to come back. This is a repeat of an earlier slide. I want to now come back to this third computer program and talk about it in more detail. This is the program to prove nonlinear inequalities by computer. There's a collection of about 500 inequalities that get used in the proof of the Kepler conjecture. Last year I did the preliminary work of just cleaning up the code and making it something, putting it in a pre-formal state, something that we might think about formalizing. There's testing of inequalities that's done at a non-rigorous level just to see if inequalities are correct. The nonlinear inequality proving is done in floating point using IEEE rounding modes, and this is now C++ code, and then I did a translation of this, at least the main body of this text, into Objective-Camel as part of preparation for formalization. So at this point last year, I turned this over to a graduate student, Alexei Solovyev, who's been very successful in doing code verification. And I should say this is similar to what I did with linear programs. So Stephen Obua in his thesis did the formal verification of the linear programming part. At least a large portion, something like 92% of the graphs that come up. And the reason, as I understand it, that he didn't do 100% of the cases that came up was that in the original 1998 proof of the Kepler conjecture, the linear programming part was done in a very interactive way. I had sessions where I would run linear programs and make adjustments and keep logs of what was going, but that wasn't a fully automated process, and we didn't have a clear specification for what it was exactly that we were trying to formalize. And so without that, it was hard to formalize something when it wasn't even clear what it was that we were trying to formalize. But so what Solovyev has done now is an automated inequality proving in whole light. It's fully functional, but not, this is recent work, it's not yet been optimized. So let me just describe the type of problems that we're trying to verify. We start with a product of integrals in Euclidean space. We have analytic functions defined on different open sets that cover the domain that we're interested in. And then we're trying to prove that for every point in the domain, there exists an index such that that point is in the domain of the function, and that function is negative on that domain. So I have a collection of about 500 inequalities of this form. And in each case, we want to prove a specific theorem that says that these inequalities hold on the domain. Most of them are fairly simple functions expressed in terms of field operations, square root, arctangent. So I just want to show you one example. I'm here this week at ICMS for a conference on foams and isoparametric inequalities. One of the problems that we've discussed this week is the optimality So we can look at different lattices in the Voronoi cell of lattices. This is what's called the body-centered cubic lattice. We have a cubic lattice, and then we add points in the centers. We can look at the Voronoi cells, and we'd like to show that in terms of surface area, this has the best possible isoperimetric inequality. So for a fixed volume, say, of 1, this has the smallest possible surface area. And so what we're trying to prove is an inequality. We can write this out. And what I'm showing you here is the formal specification of the inequality that we're trying to prove. So this looks similar to the 500 other inequalities I have, but it's more relevant this week. We have a formula for the volume. We have a formula for what we have in the surface area. This is actually whole light code. So anything that's shown here in back quotes is something that's parsed in formally into this formal mathematical system. So you shouldn't think of this as computer code as much as exact mathematical representation of some exact mathematical statement. And then given those functions, this is the value that we're trying to prove to be optimal. Again, this is in back quotes, meaning that it's an exact mathematical value. And then we give information about the domain. To the people here in this audience, gave me the estimates that I needed to insert the upper bounds on the domain this week. So this is what I get, an upper bound of 81. And then either the volume constraint doesn't hold, or we have our inequality on the surface area that we're looking for. So this is an example of a formally specified inequality. And then what we want to do is to have a fully automated procedure that goes from the specification of the inequality now to a proof inside this formal proof system. Here's another example just to show you the type of inequalities. This is not in whole light code, but it's been translated into more mathematical type language. We have a polynomial. We have partial derivatives of the polynomial. We take arctangents and pies. And then we want to know that on a certain compact domain, this function, which is the dihedral angle of a tetrahedron, satisfies a certain inequality. So the way the C++ code works is that the arithmetic is done with IEEE directed rounding. Real numbers are bracketed between a lower and upper bound. The lower and upper bounds are floating point numbers, and the real numbers are unspecified in between. Analytic functions are approximated by Taylor functions with rigorous bounds on the derivatives. For us, it's enough to take linear approximations with a quadratic bound on the error. And the domain often, when you try it on the full domain, you don't get good enough inequalities, but you find that by subdividing the domain, you get increasingly good Taylor approximations, and you just repeatedly divide until you get sufficiently good bounds to prove the inequalities that you want. And then the code is optimized in various ways. For instance, if you know that a function is monotonic, then the function is negative on the domain. If it's negative, say it's increasing on the right-hand endpoint. So now I'm going to talk a little bit about the work of this graduate student, Solovyev, on formalizing this inside whole light. The first thing he needs is fast arithmetic inside this theorem prover. As I said, you don't verify the algorithm and then run the algorithm. Every separate multiplication needs to be formally proved as you go. And so efficiency becomes a big issue. The first thing he did, and we don't need high precision, so things like fast Fourier transform methods for multiplication aren't going to be relevant here. We want low precision, highly efficient multiplication. So the first thing he did was just increasing the base from base 2 representation of the numbers to something like, base 1,000 representation. Then you build a big multiplication table, put it in a hash table, and you've worked out all the multiplications that you need in advance. And then instead of proving everything as you go, you just look up the answers in your table to do the multiplication. So this is just, you just prove the usual theorems about addition and multiplication and so forth, and they all become part of the system. So he did a few benchmarks just to compare with, and he gets a pretty good speed up from, so this is just the whole light internal multiplication that John Harrison implemented with binary and with 25 digits, so we get some speed up at least. Then the next thing you want to do is to go from arithmetic to floating point numbers. So we put an internal representation of floating point numbers into the whole light system with a mantissa, an exponent, and sign, and then prove various theorems about that. We want to use this eventually with interval arithmetic, and so what we want to prove are inequalities when we multiply rather than exact equalities with directed rounding. So just a couple of examples of theorems that we prove. There are some differences in doing this inside whole light rather than doing it just in hardware. For instance, to do a division, divisions are very cheap inside whole light because we can just multiply back out and check the answer. And so we don't actually ever do a division inside whole light. Or taking a square root, we don't actually compute the square root inside whole light. We just compute it outside and check the answer inside. So things like the computation of arctangents. Normally we would think of it as being inefficient to use half-angle identity for reducing the argument of an arctangent because it involves the extraction of a square root. But it turns out to be fairly efficient to do it inside whole light because extraction of square roots, for instance, is cheap. So we just do argument reduction and then Taylor expansion to get to compute arctangents. Then from floating point, we want to go to interval arithmetic. Again, this is similar to what you do in the C++ code, but we've now translated this into the formal proof system. One of the big strategies in doing formal proofs efficiently is that you don't want your theorem prover to actually be proving search results. So you want to do all of the searching outside of the formal proof system using efficient algorithms, and then you just want to have the search produce some sort of certificate that you then import and use, and then just verify the certificate inside the formal proof system for matters of efficiency. And so Solovyev has taken the objective camel code that is the translation of the C++ code, and he basically just traces out the steps of that execution, and anytime there's a search, he just records the results of that search so that he has an efficient record of exactly how the computation goes on the outside, and then he doesn't repeat any of that searching when he goes on the inside. So he keeps track. So for instance, I just want to, I gave a disjunction of various functions, and on each point in the domain, I just have to find one of those functions that satisfies the inequality. That's all pre-recorded and then just played back inside the proof assistant. So he did some examples with polynomials. Here are some of the test polynomials. He got these from a collection of, a published collection of inequalities that people used with a different theorem prover called PVS. And he just compared that. So this is, I won't describe the algorithm of this other paper. So you can use Bernstein polynomials to produce upper and lower bounds on polynomials. So you can prove inequalities in polynomials using Bernstein approximations. These are some of the sample problems. These are the times that it took to do the formal verifications in this other system, PVS, using this different algorithm. And these are the times that Solovyev used inside whole light. On the problems with a small number of variables, whole light seems to be doing worse than this other system. As the number of variables goes up, the whole light implementation seems to be doing much better. And one thing is that this PVS system is using ordinary native machine floating point to do the calculations without verification. So there's part in this other proof system, part of the verification is, part of it is not actually being verified because the floating point is not being verified. And that's giving them a big advantage over us. So even with that advantage, we're doing quite well inside the whole light system. So these are just the references to the Bernstein polynomial approach. Verification of Fleischbeck inequalities. Here's one example, or a couple of examples. One verifying that a certain polynomial is positive. This one he was able to do in 26 seconds. The second test took about 13.5 hours. So this is still before optimization. There's certain easy optimizations that he hasn't done, like the fact that this is still using binary arithmetic rather than, a big hash table of multiplication. It's not doing easy optimizations like the fact that the ij partial derivative is equal to the ji partial derivative. There's a bunch of easy things that can still be done. But still, it's taking quite a bit of time still to do. And we have 500 of these to do. So we're hoping for the best. Here are a few of his optimization strategies. These haven't been implemented yet. Caching the arithmetic. A lot of these inequalities, they come from the same problem domain. They're all based on the same problem in discrete geometry of proving the Kepler conjecture. And many of them have very closely related structure. They use the same functions, dihedral angles and volumes and solid angles over and over again. And so things that you compute for one inequality, you shouldn't recompute when you go to do the second inequality. So he hopes that by combining these into large batches, it might be slow for an individual inequality, but by batching them, you can do them together. And then another thing that you can do is, like I say, you don't need high precision for these calculations. In practice, in principle, it's possible to calculate the number of digits that you would need for each separate calculation and adapt that as you go and not use any more digits than really required. This is still uncompiled code, so he's going to get another order of magnitude when this gets compiled. There are various other strategies. So I've always viewed this as the hardest part of the project, is getting the formal verification and the nonlinear inequalities to work, just because I knew originally that this calculation took 3 months in a highly optimized code in C++, and I knew it would be a very big challenge to try to get this to work inside whole light, where you're checking every single multiplication as you go. But I'm cautiously optimistic that we might be able to get this all to run inside whole light at this point, just by throwing enough computers at it at the end after we've done the optimizations that we can. At the very worst, we'll have to, I think, have to do what they did in PVS, and that is to allow some arithmetic that's done in hardware. But I think that's, I'm hoping we won't have to do that. So just finally, I'll say a few words about the linear programming part. I mentioned that Stephen in his thesis did a large fraction of the cases. Here's some of the benchmarks from his from the appendix to his thesis showing the times that things take. Another thing that Solovyev has done is to really go back, and so this is all before optimization. He's gone back and really aggressively optimized all of the linear programs. And he's, so these are the times in minutes. They average about 20 minutes. He's been able to bring it down to about 5 seconds now per linear program inside whole light. Again, these are medium-sized linear programs. They tend to be linear programs involving about 1,000 variables, 1,000 unknowns. Doing it in 5 seconds is actually comparable to the execution times that I was getting 10 years ago outside of formal proof systems. So this is certainly more than adequate for what we need for the FlySpec project, and it may be useful for other people as well who want formal verifications of linear programs. He's now developed that to the point where he can do that very efficiently inside a formal proof system in a completely automated way. So thank you very much.
When you reported the reservations that your fellow mathematicians had about computer proofs, there was issues about correctness that were most in their mind, or that they most reported. But I wonder whether that's everything, because it seems to me that mathematicians, when they look at a new proof, especially something of such a long-standing open conjecture, they're expecting some novelty in the proof, and what they really want to do is understand the proof process, the sort of outline of the proof, so that they can then internalize that and adopt it for their own purposes. And I'm not sure whether they're going to be able to get that from the FlySpec project, or whether you think that's important, and how you think you might provide such an overview.
So this is certainly something that came up in the referee reports. Since it was a very long computation and it had a lot of very technical parts to it, some people had a hard time just forming a global picture of how all the pieces fit together. I don't think people would have the same problem now. As I say, the proof is, every aspect of the proof has been reworked as part of this project. And to my mind, at least, this book giving the formal blueprint of the proof is pretty clear. I think, and it goes back all the way back to the results in trigonometry that you need. So I don't think that objection would now exist.
So typically when you're writing geometry proofs, there's a lot of intuition involved, and sometimes things that people think are geometrically obvious, there really isn't a proof there at all. So in formalizing your proof, was it ever a major difficulty to fill in all of those details?
There are a few places where I was surprised. For instance, there's a library of results that we need about partitions of space, the Voronoi partition, Rogers simplices, Delaunay dual properties, and These were all things I thought were fairly obvious. It was more work than I expected to write all of that out carefully. There were some places in the original proof where I wasn't even clear to myself in the beginning what is needed. Like, I did a formal proof of the Jordan curve theorem, thinking that that would be very important as part of the proof of the Kepler conjecture. As I simplified things, that turned out to be almost entirely irrelevant to the proof. And I was very unclear, for instance, about exactly what I would need in measure theory. It turns out that I only need to take volumes of very simple things like balls and tetrahedra. The measure theory turned out to be really quite simple. So there again, the results about balls and things was simple, but the development that John Harrison contributed a great deal to this project, and developing the gauge integration and everything inside the formal proof system was a lot of work. And so the difficulty isn't always where you think it will be.
Now, I've got a question about, I suppose, convincing a computer scientist that you have a proof. So there's two parts. One is, I mean, at the end of this, I guess, I mean, will you be able to make available a zip file of OCaml code that could run with Hall light that I could scrutinize and then maybe run on EC2 or somewhere on the cloud to actually do the computation? And then afterwards, the second point is, people who use the Koch prover love the fact that it can produce a certificate that could be checked subsequently by someone else with a, small program. And Hall light, it does have a small TCB, but it doesn't give you a certificate in the same sense. And I wonder if you, I mean, would it be good to have, I mean, would you be happy to have a certificate as well, or how do you feel about the difference?
So as far as the first question goes, this is a Google Code project. It's available for anybody to download and run anytime. It takes about an hour to run the project up to what we have. In terms of, right, so the LCF style is to have a small proof kernel, and then you run everything through that kernel. There's been some talk about exporting the proof to other systems, such as Isabelle or Whole Zero, once the proof is complete, but I don't think we have any definite plans at this point.
So the whole computation will just be about an hour on a single machine?
Yes.
Wow.
That doesn't include the code verification part. So the graph generator, I think that's about 8 hours to do that. The linear programs is 5 seconds times 100,000, and then and then we still don't know. We haven't done the optimization yet on the nonlinear inequality proving, so I can't really tell you. I can give an upper bound of 500,000 hours, but I can't tell you what this number is going to turn out to be.
I'm a bit confused about, in your formalization of proofs of these inequalities, why you need to bother to formalize a particular IEEE standard floating point form, because that seems to be completely extraneous to what you're trying to prove. You could take some big int representation of the rational approximations that you're going to, but why do you do IEEE floating point?
So you're asking why we do this inside whole light. Part of it is the design of the system. I mean, once you compromise whole light, by, I guess you could add some external axiom or something that allows you to put a floating point in. But then you just have to convince mathematicians that you haven't done anything serious to compromise the system when you do that.
I'm confused. I mean, in some sense, not bringing in some particular but kind of technical standard of floating point numbers would be, in some sense, more convincing, because you have to discuss issues of round-off error and so forth, whereas if you just have representations of rationals as ratios of integers, represented exactly, and those rationals are suitable approximations to the values that you're trying to approximate. I mean,
exact rational arithmetic is far too slow for what we want to do. We can do it much faster with a floating point representation. Very quickly, you get huge denominators.
Okay, so you need the floating point representations.
I'm curious about the part of the text that hasn't been verified yet. You said that almost all of it has been. What slows down the part that's not been?
So I would say the biggest factor is that my NSF grant ran out. So we have a smaller group now working on it than we did before. There's nothing in what remains that I have any concern about. It's, as far as I see, it's just more of the same.
So you mentioned this algorithm that started out at 170,000 lines, and that Tobias worked on it, got down to 10,000. And that at the same time, the runtime went, I think it was, you said, went from 3 months to 1 day?
Yes.
So I'm thinking, wow, what a great example to show my students. Look, you can shorten something from 170,000 lines to 10,000, and it gets 90 times faster. But then I remembered that this was over a period of 14 years.
Yes.
And of course, over that period of time, computers got 500 times faster, I think. So is that why the runtime went down, or?
That is certainly a factor, but I can claim credit for part of that optimization. Yeah, one way that you can optimize inside whole light that you can't do outside is that you know that the computation inside whole light is going to be very long, and so you can afford to do some so it doesn't make, if you have a 12-hour computation, it doesn't make sense to do 20 hours of computation to see how to make it run faster. But if you have an extremely long computation in whole light, then it does make sense to do these other things to optimize.
We may ask you something quickly. So you mentioned that you proved 2 conjectures along the way, and that was through revising and looking at the proof through the lens of the theorem prover. But and you presented these results, I assume, and have them accepted for publication. Did you emphasize any of these aspects to do with formal verification or formalized mathematics when in these papers that you've had? I mean, to the mathematical community again.
So one reference for these results is the last chapter of the blueprint book. So you sort of go through the blueprint of the Kepler conjecture, and then there's this one extra chapter at the end. That so there you see very specifically how those new proofs relate to the formal proof.
So I think we should thank Tom again for giving us an entertaining talk. By the way, there's a reception in the forum right now on level 4, so please feel free to join us and talk more to Tom about anything else you want to discuss. Thank you again, Tom.
This production is brought to you by the University of Edinburgh.